Okay, take your attendance. Okay, class. So let's start our lesson. Okay, today our plan is, of course, we're done with the topic. Today we do more questions about the astrophysics and of course cosmology. We try to get some rough idea. We do questions about that. Okay. Before we continue, we go for kind of a summary first. Summary first. What you learned about astrophysics and astronomy and cosmology. Okay. So let's recap. So what you learned? Astrophysics, new topic. So what are the formulas you learn? Can recall? The first thing you learn about flux equals to what is that? Luminosity over 4 pi d squared. So if we are at the surface of the Earth and there is a star as a luminosity of certain value, so the Earth and the star distance is d. So we get a certain flux. Flux means the intensity of light we receive from that star is connected with this first formula, right? Okay. So second formula you learn is the Wien's law, right? Wien's law. Wien's law talk about the black body. So it's got talk about the black body radiation. So you see, if you have a black body, then it has a surface temperature of T. Then it give out, of course, EM radiation will be emitted due to its thermal energy. So a range of wavelength will be emitted. A range of wavelength. So the peak wavelength is found to be proportional, inversely proportional to the surface temperature of the black body. So leads to the second formula, right? So lambda PT is found to be constant, Wien's law. Okay. And the third we talk about Stefan Boltzmann, Stefan law. It is also something to do with black body, and found that the luminosity. Actually, for the case of black body, the intensity for a black body again, the intensity at its surface, black body, the intensity of the radiation at the surface is, he said, is proportional to the T power of 4. Okay, T power of 4. Okay, it's T power of 4. So when we equate, we found a constant sigma T power of 4. And if this, when we adapt this system to the star, the intensity become, of course, intensity knows power over area. It's a sigma T power of 4. So for a star, the power is the luminosity. So end up getting sigma A T power of 4. So this is the third formula by using Stefan Boltzmann law. Okay, this helps us to find the area is actually the area of the star, area of the star, right? So sigma 4 pi r squared T power of 4. Okay, the third equation. Okay, and after that we come to the Abel's law. Okay, before Abel's law we learn about Doppler effect. Okay, Doppler effect for light. Doppler effect for light. What is the formula introduced? V over C is equals to changes of lambda over lambda. The fourth equation you learn. Okay, so this tells that what is the recession speed of that star if you know the wavelength. Okay, changes in wavelength. So as I said, when a star emit a certain wavelength, but by the time it reaches the surface of the Earth, the wavelength is found to be changes due to Doppler effect. Okay, because the source is moving away. So greater the changes, we call it as a redshift, right? Redshift. So shows that we can get the recession speed. Okay. Okay, I need to talk about the wavelength. I think some of you got a problem with the understanding the wavelength. Yeah, we will come back to that. Okay, let me explain here itself. Okay, some of you ask me, okay, how they got the original wavelength. Okay, we receive one wavelength here, okay, from the star, but how to know what is the original wavelength emitted by the star? So how to get the original wavelength? Okay, you should understand this. Okay, you see, our universe. So just explaining. Some of you asking this question. The WhatsApp. So in the universe, I think the 3/4 of our universe is made of hydrogen. Okay, so hydrogen particle, the smallest atom, is covers the universe about 3/4. Okay, so every star as hydrogen for sure. Okay, for our sun also, the core is turning to become helium, but surrounded by so we have hydrogens. We got hydrogens. It's full of hydrogen at the surface. Okay, so remember, in our surface of the Earth, we have hydrogen gas. So this hydrogen gas, you know your quantum physics, you know the nil ball, the energy levels. Okay, the hydrogen has its own electron, has its own energy level. So you know, right? The electron, when it transit down, it give a line spectra, right? The emission and absorption line spectra. Okay, so if the hydrogen is heated, after for a while, when the electron goes down, it give a line spectra, right? So for hydrogen, let's say it has a 4 energy level, means let's say the hydrogen has 4 energy level. 4 line will be produced. 4 line will be produced. Okay. Of course, to the right is like increasing wavelength normally. Increasing wavelength. Okay. So this hydrogen, why it forms 4 line? Maybe it has 4 energy levels. Okay. Okay. This line spectra. To understand more, this line spectra on the surface of the Earth, they're not only done for hydrogen, they're done for helium, they're done for oxygen, they're done for most of the gas particles, any elements. Maybe for calcium, let's say a calcium substance, they heated it and let it go down, so it releases EM radiation. Of course, it's not visible. So it has its own line spectra. Maybe the calcium has maybe 10 energy levels. You get 10 lines. So this line spectra is like, can we say it's like a analog to fingerprint? It's like a fingerprint, like for human. Like you and your friend. Do you have the same fingerprint? The fingerprint is your own identity, right? Okay. So for fingerprint for hydrogen is the line spectra. It never change. If hydrogen got 4 lines, means from out of space, if they receive a line spectra with 4 lines, okay, with the same interval, they know that spectra is actually originated from a hydrogen atom from that star. Okay. So when they receive, they found that the original one they're not going to get from the star. The original one they find it from the Earth itself. They just use the hydrogen atom. They find the original line spectra. Okay. This line spectra must be on the surface of the star too. Okay. This is the original. So original wavelength we can find in the lab itself on the surface of the Earth. Okay. So the one received by the star, we found that it got also 4 line, but that line has been shifted to the right. Okay. The first wavelength has been shifted to the right, all shifted to the right. It means the same fingerprint, but it's shifted to the right. It shows redshift. It's a redshift. Yeah. So remember, the original of the wavelength of the star is actually obtained from the lab on the surface of the Earth. Okay. Yeah. So they, from the star, not only one line spectra they receive. No, sometimes they get the line spectra of calcium. So they compare the line spectra of the calcium they receive with the line spectra on the lab, in the lab. So the line spectra in the lab by using the calcium is the original wavelength. Yeah. So hope you got the idea to find the original wavelength, how to get the original wavelength. Okay, so that's the fourth equation, okay, by Doppler effect. And the fifth one, Hubble's law, V equals to H naught D, the fifth equation, okay. And finally, we discussed about the Big Bang theory. Okay, so recall back all the equations. So flux, Wien's law, Stefan's law, Doppler effect, Hubble's law. Okay, Hubble's law. And finally, they use Hubble's law to find the age of the universe. Okay, so V equals to H naught D. V must be distance over time. So the distance over time must be equals to H naught over D. So the time is found to be 1 over H naught. So this should be the time of the universe. They got about 13.7 billion years. Okay, yeah. Okay. Okay, so based on this, any questions, guys? Any part you don't understand? Okay, this is what we learned so far. Okay. In the This is the specimen paper. This is the specimen paper by Cambridge. Okay. So this is how your question paper going to be as a specimen paper for 2022. This year. So I'm checked the constants provided. These are the constants provided. The only constants given for astrophysics, I think, the Stefan Boltzmann constant. Only the Stefan Boltzmann constant is provided. Wien's law is not given here. The constant of Wien's law. Okay. And the equations given for the astrophysics is the Doppler shift equation given. Yeah, the luminosity formula is given. Only these two equations given. Yeah, that's all. These are the two equations given. Okay, so looks like the Wien's law constant is not provided. So I'm expecting that if they want to make use of the Wien's law, they should provide us the constant in the question itself. But anyway, just to be safe side, okay. So remember the Wien's law constant, okay. 2.9 times 10 to the power of -3, just in case, but they should provide in the question itself, okay. Okay. So let's we go to the last part, the questions. Okay, I see.
Sir, can explain the cosmic microwave background radiation as well?
Cosmic, this one.
Yeah.
Okay, this one, they, background radiation since your O levels, right? So we found that on the Earth, from the surrounding, we are Earth. So surrounding, we receiving cosmic ray from the universe, okay, out of space. So the cosmic ray is due to the universe temperature, due to the universe temperature, because anything as more than 0 Kelvin, it has a thermal energy. The thermal, once it has a thermal energy, it give out EM radiation. It definitely give out EM radiation. So according to the Wien's law, lambda P proportional to inversely proportional to the 1 over T, the surface temperature. So the universe itself has its own temperature. So they said this is evidence of Big Bang, right? They said currently they found that the universe temperature is like 3 Kelvin. Okay, they found it's 3 Kelvin, and they found that it releasing the microwave. What do you call? The microwave radiation, it giving out microwave radiation. Okay, so they said originally when they are close by the Big Bang, when the time is 0, the temperatures of this universe is found to be very high and very highly dense. Density is very high and high temperature. So as I said, the radiation is must be in a, I don't know, it should be a gamma region maybe. Okay. So but now because it's cooling down, currently 3 Kelvin, it giving out microwave. So because it's giving out microwave for 3 Kelvin, so this supports the idea of Big Bang. Okay. Yeah. So Hangus, which part you don't understand? Yeah. So yeah, so 13.7 billion years. So now it reached 3 Kelvin. So 3 Kelvin give out microwave. That means originally together the radiation must be high. What do you call high frequency? Should be high frequency, low wavelength. But you might one of your friend asked me for this 10 years, is this temperature, is it dropping? Do they detect any other bigger wavelength? Okay, is it dropping or not? So the universe temperature currently we know is 3 Kelvin, but is it going to change 3 Kelvin to, let's say, 2.9 Kelvin, just 0.1 Kelvin differences? Is it going to take like 100 years? No, it's going to be few million years. 3 Kelvin to drop to 2.9 Kelvin. Okay, so because 13.7 billion years it took to change from I don't know what is the origin radiation it releases to achieve microwave now. So 3 Kelvin to convert to 2.9, I think take few million years. So time factor, we don't have that data. Yeah. So that's why two evidence for Big Bang is of course redshift for sure, and second is the microwave radiation, cosmic ray in form of microwave. Okay, it's evidence. Okay. Any other questions, guys, before we continue? Okay, so I just want to tell you this. This is a little out of syllabus. You see, mystery. The mystery of this this universe is a lot of mysteries, of course. Another mystery is this one. What is that? I move this. Okay, so you know, if it's Big Bang, it explodes. Now the universe is expanding. Universe is expanding. Like like an explosion, something explodes. So when the mass is all the galaxies, the matter is moving away. So the force which is moving inward should be the gravity, right? The gravity is the one moving back the matter towards the center again. Like you are throwing a ball upwards. When you throw a ball upwards, what happened to the ball? The speed of the ball should reduce, right? You go to the up, it slows down and come back again to the center of the where it was thrown. Okay, so the gravity is acting towards the center. Okay, so the galaxy, if it's moving away, what do you expect? The speed should decrease, right? Like the ball, speed should decrease when it go away. But Hubble found that the recession speed is increasing. More further it is, more greater the recession speed. So now the question is, the force is towards the center. The galaxy experiences the force towards the center because of the gravity. But it accelerates outward. It looks like it accelerates outward. The speed is increasing outward. That means the net force is not towards the center. Looks like the net force is outward. Okay. That means there is an unknown force. There is an unknown force is pulling the stars away from the center of the explosion. Okay, what causes this force? This is another mystery. What forces pulling the planet away? Okay, so we don't have answer for this force, but they said the energy which causes this force, they label it as something called dark energy. I don't know, it's very interesting fact in astronomy, but not in your syllabus. But very interesting fact to include dark energy. Okay, they say dark energy. Why they given the name dark? Because human unable to find what type of energy it is. There is a dark energy which makes it to move away, causes this force. Okay, and another stunning information is they said all the mass energy of the universe, okay, mass energy of the universe 100%. They said the dark energy consists of 67%. Okay, so the dark energy on the universe is about 67%. Okay, yeah. So, but human don't know how to harvest this energy, what causes this energy, and so on. If human able to get this energy, I think then the beginning of what we call space traveling. Okay, it's the beginning of space traveling then. So we no need to rely on the fossil fuel anymore. Spaceship with using the dark energy in the space to move forward. But still, this is a big question mark. But interesting fact: 67% of the universe energy seems dark energy. Okay. Okay. So, any other questions, guys, before we go to the questions? No, Okay. So, some questions. Okay, let's read. Use the law, you learn all the formulas. What do you think the answer for this? Question 1. X and Y are identical stars. When being viewed from the Earth, the flux from the star X is 4 times the flux from the star Y. That means, what is the conclusion mean? Star X is 4 times greater. That's the flux. The Earth flux from the star X is 4 times the flux from the star Y. That means, what is the conclusion made about X? So which is nearer? So X have to be nearer, right? Okay. So this is the Earth. So X have to be nearer because X and Y give out the same luminosity because the flux on the surface is, of course, luminosity over the 4 pi d squared. So the distance squared. Okay. So for the X and the dx, it gives 4f. 4. I put just 4. Just 4. 4f. Okay. For L over 4 pi dx squared. F for L over 4 pi dy squared, the distance of y. You rearrange this, you will find that the dy is 2 times greater than dx. Okay. So, of course, from the first A answer, you should know the y is 2 times further away from the x. How do you get to know? From the flux formula. From the flux formula. Luminosity is the same. The nearest one will give greater flux. Okay, so X star should be nearer. Y should be further. How many times? Twice. You rearrange this, you get the answer. Okay. So those who got Y is twice further away from the X, good. Those who thought of flux formula to be used, good. The part A. Okay. Okay. Any questions? A. Hope you got the idea. B. What is meant by standard candle? A standard candle is a stellar object of known Of course, the answer is what? Of course, luminosity, right? There's no one luminosity is called standard candles. Yeah. So see, standard candles enable what to be determined? Standard candles is used to find what? To find the distance, right? The distance of the star. The distance of the star from the Earth to be determined. Standard candles by using the flux formula, right? Okay, those sort of standard candles enabled for the distance to be determined. So C should be distance. Okay, think about D. What is the answer? The radiation flux intensity depends upon what and what? It's all in this formula, right? Flux is depend to luminosity and the how far the distance of the star from the Earth. Okay, so radiation flux intensity it depend to the luminosity for sure of the star, luminosity, and the distance, right? The distance of the star, distance of the star from the Earth. And the E, the frequency at which maximum radiation of energy occurs is how related to the absolute temperature, maximum radiation. Many times I told you, right? Wien's law, right? This one. So lambda P is inversely proportional to the absolute temperature of the black body, actually, black body. And this temperature we call absolute temperature, or can call thermodynamic temperature, temperature in Kelvin. Okay, good. Those who predicted correctly. So this should be the answers, right? Okay, so first question testing flux and the Wien's law. Okay, so any questions? No problem. Okay, so remember the 4 to 5 equations in your mind. Okay, we go to the next question. Decide which formula to be used, how to go about. Okay. Okay, next one. Okay, 2 minutes for you. Figure out which formula to be used. Is it the Wien's law, Stefan's law? Is it the Doppler effect? Or is it the Hubble's law? Which to be used for this case? Or the flux equation? You got 5 right altogether. Flux, Wien's law, Stefan, Doppler's effect, and Hubble's law. 5 formulas. Okay. So the sun behaves as an approximate black body radiator with peak energy radiation occurring at this wavelength. Okay, so this star, our sun, has a peak wavelength of this much, like this your lambda P. Show that the sun has a surface temperature of 6,000 Kelvin. So of course this is Wien's law, right? This is Wien's law. Yeah. So of course lambda P multiplied by the temperature should be the constant. How much is the constant? Look like your actual examination, the constant not provided. So remember the constant. What's the constant for the Wien's law? 2.3, right? 2.3 times 10 power negative 3. Yeah. Sorry, 2.9 times 10 power negative 3. Just in case, memorize it. Wien's law constant. 2.9 times 10 power negative 3. Yeah, use that. Get the surface temperature. So lambda T equals to 2.9 times 10 power negative 3 to be used. To get the T, should get 6,000 Kelvin. Okay. Okay, next. The radiation. Okay, I hope you got the answer. One is just Wien's law, right? Okay. You come on, another 1 minute. Figure out which formula to be used for the 2 and 3. The radiation received from the sun at the top of the atmosphere is this much. Okay. So this is the radiation received from the sun. Okay. So this is your flux, right? This is your flux. Okay, so flux. Distance from the sun and the earth is this much. This is your D. So show that the sun luminosity is this. So they're asking, prove that luminosity is this much. So looking for luminosity. So I think which formula comes to your mind? Of course, flux graph equation again, right? Flux equals to luminosity over 4 pi d squared. So you know the flux, you know the d, you know the d, right? Yeah, d given. Where's the d? Yeah, d given. Yeah, you can find the luminosity. You can get the luminosity. Okay. Just get the which formula to be used. I don't need to calculate. Okay, so first is Wien's law, second is the flux formula. Okay, so third one, hence calculate the radius of the sun. So how do you find the radius of the sun? What formula comes to your mind? This is Stefan law, right? Stefan Boltzmann law, right? So what formula Stefan proposed? The intensity, the power over area of the black body is directly proportional to the T power of 4. That the thermodynamic temperature power of 4. Okay. This leads to what formula? We change to luminosity. So luminosity is found to be sigma A T power of 4. Okay, we stick with this formula. So Stefan law. Yeah, from here you can find the radius, right? The radius is under A, right? 4 pi r, the 4 pi, 4 pi r squared. The r is the radius of the sun. Luminosity, you know. Temperature, surface temperature, you know, at part 1, 6000 Kelvin. So you can find the r. Okay. So question 2, I think linking to flux, Wien's law, and Stefan's law. These three has been tested. Right. So of course, this is the working, right? Must be in your mind. First one is lambda T is 2.9 times 10 power negative 3. You can find the surface temperature. And the second one, we want to find the D, the sun and the earth distance. So we use flux formula, luminosity over 4 pi d squared. Prove the luminosity. Then finally, how far away the sun from the earth, the surface of the sun, the radius of the sun. We use the Stefan law. Luminosity is sigma A T power of 4. A is 4 pi r squared. The r is the radius of the sun. So you can work out. Okay. So hope you got the idea. Any questions? Stop me. Okay. So we go more questions. So we go to the next question. Figure out which formula, how do you go about? Okay. Ready? So we go to the third one. Okay, third one. Okay, read the question. Just spend 2 minutes. Figure out what formula to use. How are you going to go about these questions? So remember, the first question is first equation is what? Flux is luminosity over 4 pi d squared. Second one is Wien's law, lambda pt is constant. Third one is Stefan Boltzmann. Luminosity is sigma A T power of 4. Fourth one is Doppler's effect. P over C is changes of lambda over lambda. And fifth one is the Hubble constant, Hubble's law, V H naught D. So which formula do you think suitable here? The surface temperature of radius of sun, or T given temperature, or radius of the sun also given. Okay, respectively. Calculate the luminosity of the sun. So which formula to be used? course, the Stefan law. Stefan law is used. Okay. So third equation must come to your mind, right? Yeah, luminosity is sigma A T power of 4. You know T, you know the R, so you know the constant, so you can find the luminosity. Should get 4 times 10 to the power 26. Okay, the first question, Stefan law to be used. Okay. Okay, look at B. What formula to be used for B? Calculate the radiation flux. Calculate the radiation flux. Oh, this is F law. So the only equation with flux is, I think, the first one, right? Yeah, first one. Okay, calculate the radiation flux from the sun at the top of the Earth atmosphere. The distance from sun to Earth is 1.5 times 10 to the power 11. So this is your D, right? So D is given. They are asking flux. So you know D, you know luminosity already from part A. So we can find the flux. So first equation. Okay, second one, B must be the flux formula. Okay, so thought of first equation, good. Okay, C. This is okay. Look at C. Okay, this is a qualitative question. Suggest why the total rate at which energy from the sun arrives at the top of the Earth atmosphere is much less than F times A. We know F times A is the luminosity, right? Is the luminosity. Okay. Yeah. So where A is the area of the spherical surface representing the top of the atmosphere. The top of the atmosphere. Yeah. So any reason why the flux we receive arrives at the top of the Earth's surface is much less than F times A. The sun arrives at the top of why the total rate at which the energy from the sun arrives at the top of Earth atmosphere is much less than F times A. What's the reason? Okay, the reason may be some this is caused by flux, flux times A. The area of the Earth may be because only the half of the Earth is exposed. Or, yeah, we can't say that. Any answers? Which energy from the sun arrive at the top? The flux, of course, the flux we receive is sorry, the flux we receive is smaller than supposed to be. Why smaller? Because some energy will be absorbed by the dust and the dust in between the movement. Okay. So you check the answer here. The idea that the calculated F is from the, this is another one reason. The flux is always 90 degrees from the surface. Okay. But at the Earth, the flux never reach. It's not normal. The flux we are getting is not normal from this surface. It like we need to get the flux which is 90 degrees. The idea that the calculated value F is for radiation meeting the atmosphere at 90 degrees, which is only true one place, only at the above the equator. Yes, but if it's above the North Pole, I think the flux is not 90 degrees to the surface. Yeah, then only half part of the Earth is illuminated by the sun at any one time. Okay. Yeah, so this is the reasons. Okay. So only 3 questions here. I posted a list of questions on the just added into the times. Okay. If you go back to times, okay. Yeah, so I added 2 documents here. Last time just the, what do you call, just the PowerPoint. So I put the Word file, astronomy and cosmology, and questions here. You have some questions here, about 20 over questions. You can give a try this question later. Okay, and I add another two documents here for medical. Okay, medical physics and past year compilation. So for ultrasound and X-ray, but these 2 documents don't have answer yet. But the year is stated. You try these questions first. By next week, I think by Tuesday, I post the answer for this medical. Okay. Any questions? So this question I don't want to explore now. You can explore later. There are a few questions here, 20 over. I go to the exam mate. Okay. After you gone through this document, these questions, you can go to exam mate as usual. Okay. You can go to exam mate, but exam mate, of course, Cambridge just introduced this topic this year. But Edexcel, so you go to Edexcel, select Edexcel. Edexcel doing this topic for a long period of time. So you go for A-level Edexcel, okay. Of course, subject physics, go to physics. And you no need to select, so go to the topic. So scroll down. So go for, space and astronomy. You click, okay, so you will get questions from astronomy, okay. But one problem here is that Excel doing more than what you are doing now in your Cambridge. I would say like 60%, 60 to 70%, not even 70, around 65% of what Edexcel learning about astronomy you are doing now. Okay, so some questions are not into your syllabus. Okay, so that's why you need to select the questions. Something you feel you never learned before, like dark matter, dark energy, something called like this. If you have a graph like this is not in your syllabus. This is not in your syllabus. This is called Earth-sprung vessel. For you, it's out of syllabus. So any graph like this, you can skip. Okay. So let me select some questions from here. The one linked to your syllabus. So this is not in your syllabus. You go down. Of course, objective. You can give a try. Your paper is structure. Okay. So which letter region of diagram? Oh, this also related to the graph. So we skip this. This could be your question. Okay, well, let's give a try. Okay, as usual, guys, come on, think about what formula is suitable. Give a try this question. I give you 2 minutes. Which formula is? How are you going to deal with this question? So Vietnam, battle, what is our nearest red giant? It's a star, red giant. Star got different names, different sizes. The name given depend to the size. Red giants are quite a big star. So it's just take it as a star. It has a luminosity of this much, 4.49. It emits the radiation with a peak energy emission with 850 nanometer. Show that this red giant has a surface temperature of 300 Kelvin. So what formula to be used? So Wien's law, right? You know the power, you know the luminosity. Oh, sorry. You know the luminosity, you know the peak wavelength. You know the peak wavelength, you can find surface temperature already. Lambda T equals to the constant, right? 2.9 times 10 power of 3, right? So you get that answer. Okay. So first one is the Wien's law to find the surface temperature. Correct? Okay, next, can you figure out how to find the radius? Hence, calculate the ratio of the radius of that red giant, RB, to the radius of the sun. Okay, this question, I think maybe at Excel, the radius sun need to be given in the exam. That's why they never stated the radius of the sun. But if it's in Cambridge, they must give the radius of the sun for us to compare. Okay. So first of all, let's say assume the radius of the sun is provided. How are you going to find the? Oh yeah, radius of the sun is given. What I'm doing. So RS is given. So find the RB. So find the RB, then you ratio, you get the answer. So how do you get RB? What formula? Anybody? What formula? So Stefan's law, right? You know luminosity. You know temperature. You can find the radius by using Stefan's law, right? Lambda equals to what? Sorry, sigma. So use Stefan's law to get the answer. Then get the ratio. So this formula, this question is about Wien's law and Stefan's law. Okay. Okay, we go to the answer. Check. So yeah, the first part, lambda T is equals to the constant. So you get the surface temperature. Then we use the Stefan's law. Luminosity is the area sigma T power of 4. T, yeah, we are looking for the radius now, right? Radius, you get the RB. Once you got RB divided by RS, you get the ratio. Okay. So Stefan's law and Wien's law again. Okay, any questions? No questions. Yes. Let me go and check the question linked to Hubble. We haven't do much about Hubble with the Doppler. Let me check any questions with Hubble. Yeah, this is good. Okay. Okay, yeah. Yes, come and give a try. Okay, so how do you do this question? Okay, so this is the recession speed with the distance, right? The galaxy. Okay, the graph shows how the velocity varies with the distance for number of distant galaxies. All the galaxies are receding from the Earth. There's appears linear relationship. Okay, we know the story. Okay, use the graph to estimate an age for this universe. 4 marks. So how do you do this? Anybody? Any idea? Okay. Riyad, you have any idea? Any formulas to be used? Riyad, not here. Okay. Ashley? 1 over h naught. So you find the, how do you find the h naught? The gradient, right? Yeah. Yeah, good. So you find the h naught from this gradient. Say gradient is 4 marks. So first you say the gradient is the h naught. Then of course, don't straight go to the VHT, right? So yeah, so calculate the gradient of the line. Identify that's V equals to h naught d. So the gradient is h naught. Then t is 1 over h. Yeah, so you get the time. You use time. Okay, I want to state something. I want to state something just in case if they ask in exam. You see, this is also a little out of syllabus, but you see, is the what do you call? It's like a balloon expanding, right? I told you like a 2 point is like a 2 galaxy. So it expands this distance, which is at the beginning the A and B like in a same location. So when the time runs, they just spreads. They spreads, and we found the drift speed at this location at this moment, and so we use v over v equals to, of course, h naught d, and the v is distance over time. So we say this time is the time it traveled from the beginning to the end. Okay, but this is only correct by assuming that the rate, remember, the rate of expansion is constant. We are assuming this answer is only based on the rate of expansion is constant. That means the distance increases with the same speed. The same speed. That means the VD is like constant, but in reality, the VD when go further get greater. Okay. Yeah. So if they ask, this answers only by assuming the rate of expansion is constant. Based on that, we get this energy of this universe. I mean, the time of the universe. Okay. So please include your notes. The answer we got is based on one assumption: the rate of expansion is constant. Okay. Okay. So yeah, we go back. So we go more Doppler. I mean Hubble. So this graph is not in your syllabus. Yeah, this is not really going to Hubble. This is another Wien's law, right? Okay, this is different. Let's go ahead. So the graph shows how a emissive power varies with the wavelength of the star surface temperature 5,500. So on the same axis, sketch graph to show how the power, the emissive power, the wavelength for the star with surface temperature of 5,000 and 6,000. Okay, you know, right? The graph is shifting to the peak shift to the left, right, for the higher temperature. Okay, so yeah, you should know how to draw, right? Okay. Yeah, for 6,000, of course, it's getting greater, but the peak is going to the left. For this should be for 6,000, and yeah, 5,000 is somewhere here. The peak is like this, right? Okay, so this for the 5,000. Okay, so remember the Wien's law and the graph. Okay, yeah, so that's it. Okay, let me check for the. This is, I would say, same luminosity flux question. We did many times. We skip this. No, this one. This, you see, these questions also. You know, at Excel they learn the astrophysics and the gravity together. So some questions will involve astrophysics together with, you know, the Newton's law, GMM or R squared will be linked. So question like this you can do because gravity also in your syllabus. Okay, so but I skip for time being. I don't want gravity for time being. Okay, this question, come on. Okay, of course, no objective for your exam paper, but what do you think? What answer you think logical? 1 minute for you. Light from a distant galaxy is analyzed. The line spectrum obtained is compared with a similar radiation from the sun. When compared with the light from the sun, a line in the spectrum of light from the distant galaxy as a, what do you think? Which is a possible answer. So, of course, we know the universe is expanding, right? The universe is expanding. So of course, wavelength should get longer, right? The redshift. So wavelength get longer, but frequency should get lower, right? The frequency received should get lower. Wavelength longer, frequency is lower. So answer C or D. But your quantum physics knowledge, you know, right? What happened to the photon energy? Photon energy, what's the formula? HCO lambda or HF, right? So low frequency means photon energy also low, right? HF, but so low F means low photon energy. So those who predicted D is good. The answer should be D, right? Low frequency, smaller photon energy, correct? Yeah, it should be D. Okay. Yeah. So you have lots of questions, but you have to select. Okay, you have to select the questions. You can give a try from exam mate to go to Edexcel, go to physics, go to space astronomy. Don't anything to do with the antimatter, dark energy, dark matter. That's all not in your syllabus. The Hertzsprung-Russell, the graph, it's not in the syllabus. Anything to do with Hubble, yes. Okay. Anything to do with the luminosity flux, yes, it's in your syllabus. Okay. Okay, class. So what we're going to do next week, Monday, is we'll be going through. If you got any question after you've done the topical questions for the topic 15 and 14, we check on Monday. If you don't have, I'll be exploring the trial paper. Yeah. So A2 trial paper got paper 4 here. So we explore from the bottom. Maybe the last two papers we explore from the circular motion to here, if you have any. So on Monday, on Monday onwards, going to be your turn. You're going to ask me questions. Anything you don't understand, we discuss. Okay, can be from trial, can be from the actual paper. Okay. Oh yes, time's up. So I stop here. So as usual, if any questions, can stay back. Those who don't have can leave. Thanks.